Hi, in this video I want to open one of these spark generators and we are going to look at the internal circuitry of the generators. They are normally sold as 400 kilovolt high voltage modules, but probably they are 20 to 30 kilovolts devices. Internal structure, I partially know what is there. It's basically similar to these arc generators. So there is an oscillator circuit here, and then there is a step-up transformer, exact things that we have here. But in these spark generators, there is also a voltage multiplier after that transformer. So basically the voltage will be rectified and the magnitude will increase. So the high voltage that we produce at these terminals is higher than what we have in these arc generators. And this one is DC, this one is high voltage AC. Here I have two of them. One of them is actually partially damaged and one of them is functioning good. So I'm going to show you the failure mode. Basically, if I apply voltage to this one that is partially damaged, we notice that the arc frequency, the spark frequency is very small. So it cannot basically produce sparks very quickly. But the other one that is new, if I connect it to a battery, we see that that one produces sparks much faster. This suggests me that probably on the voltage multiplier section that we have at the end of it, one of the capacitors, they are damaged, and that's why this generator cannot produce higher voltage and the repetition rate decreases. This one probably produces 20 to 30 kilovolts, and those capacitors that are placed in these voltage multipliers, they are maybe rated for 10 to 20 kilovolt. So if the terminals are kept far away and you apply few volts to this with high current, sufficient current, few amps, then those capacitors will get really stressed and they go to their limit. So if you repeat this process multiple times, eventually you're going to break those capacitors inside this voltage multiplier. So I guess that is the reason why this generator does not work properly. And of course, there is a challenge to remove this epoxy properly without damaging the circuit. In many cases, you have a switch or you have an electronic device that is potted, and maybe we want to understand what is that circuitry, so we want to remove the epoxy from it. I'm going to think which method I should use to remove the epoxy properly. Maybe I immerse it inside acetone, and or maybe I put it in hot water or hot oil. We will see which one will work. So I'm going to remove this cover first, and then we'll take a few samples of epoxy, and then we'll test different methods on those samples. Whatever method that softens the epoxy the best, I will use that method to remove the rest of the epoxy from this module. And then we will see the internal circuitry. Okay, so now I can easily remove this part, which will come out. Okay, so I have to remove this top part, that's okay, and then I will create another cut here. Okay, so plastic cover is now broken, and we will see how to take sample of epoxy and test it. Okay, so I'm going to take some sample from this part of the epoxy. Hopefully there is no circuit in this section, and then we will test the epoxy with different methods. So far it seems that we have not damaged the circuit, and I have a sample of epoxy. Okay, so the plastic cover is removed, and I also saw the piece of epoxy from the sample. After cleaning it, I noticed that the saw almost hit to the circuitry, so there is a piece of metal there. I'm going to test the circuit again to see whether it works or not. So still it produces spark. It means that I did not cut through the circuit completely, so it's okay. I will test this sample with acetone first and see whether acetone can soften this epoxy or not. Okay, so I poured a bit of acetone inside this container, And I'm going to put this sample inside and leave it for some time. Then I will open it and check whether the sample is softened or not. Okay, so it's almost 2 days has passed since I put this piece of epoxy inside acetone. Now I'm going to open it and we will see whether anything special happened to this piece of epoxy or not. So this is the epoxy. Okay, so certainly it is softened and it becomes very brittle. So I assume that if I leave that piece inside acetone for more days, then it would be easy to remove epoxy from it. So now I'm going to put this one inside acetone and leave it for several days. Okay, so I put this generator inside this tube. This one has a small volume and this one almost tightly fit into it. So I need to pour only a little acetone through it to cover all of it, and then I will leave it for a few days such that epoxy gets softened, and then I will try to remove the epoxy. So now the acetone is in. I'm going to close this and leave it. Alright, so it's now 4 days has passed since I put the generator inside this box. Now I'm going to remove it and we see whether we have anything special or not. You see this red wire now becomes completely white. Okay, so let us see. Okay, it breaks a bit. So this wire is going to there. That is interesting. Damn it. It break. These are some capacitors, obviously, because it also damaged the components that are inside this module. So was not a very brilliant idea. I should have used a pair of gloves. Now this acetone is penetrating my skin. So we see that inside there is one of those transformers. So the circuitry is exactly the same as those arc generator, at least from the step-up transformer point of view. It's completely the same. We also have the resistor and the diode. So those are also the same. There we have this tiny transistor. What is this component? It's this is the discharging resistor, I think. Probably, or something. Is it that it has a discharging resistor at the end? Okay. So these are those capacitor from voltage multiplier, I assume, but we will see. Okay, so I've removed most of epoxy from these components. Here are the input terminals. We have the primary side, which is an oscillator. So this is almost the same as the previous arc generator, which I made a while back. Now the only difference is that here we have a capacitor between drain and source of this transistor. In the arc generator, we do not have that capacitor. Because here when we have a DC at the end and then there is a short circuit, a disturbance will happen which causes an overvoltage on this transistor. So this capacitor will capture that peak overvoltage. Now we have this step-up transformer which amplifies the voltage maybe 200 times, 250 times, and then it comes to this stage, which is a voltage multiplier. Now this voltage multiplier, it has, as you can see, it has 3 diodes, 2 blue capacitors, and actually these 3 capacitors, these are red capacitors, they are connected in series, and they are connected at the terminal of these voltage multipliers. So we have totally 3 capacitors, so this is 1, this is 2, this is 3, and we have 3 diodes, so this is a voltage tripler. So basically we will have around maybe 6 to 8 kilovolts at the terminal of this transformer, and then that will be multiplied by 3, roughly 24, but of course the efficiency is a little bit less, so maybe we get 20, 22 kilovolts at the terminal of this. Okay, so let me measure the components and I show you some of the values. Okay, so let me measure these capacitors. There are 3 of them in series. So this one, it gives us approximately 7.6 nanofarad. The other one gives us around 7.4 nanofarad. And this last one is 7 nanofarad. Okay, so now these capacitors, probably all of them should have equal value, maybe 7.5 or maybe 8.2 or maybe 6.8 nanofarad, one of these values. I don't know which one is true, but it's in that range, and they are connected in series like that. Now if I measure the capacitance of one of these blue capacitors, it's a bit complex because the terminals are separated. So we see that this capacitance is approximately 105, and the other one is almost the same, so 100 picofarad. And then we have these 3 diodes. So the resistor here, this one is, it should be simple, so this is 28.5, and this other capacitor, so now I have to wait to stabilize this capacitance measurement, but okay, I just do it, doesn't matter much. This is maybe high value of capacitance. How much is this? This is 49. Okay, so I have to reduce also the capacitance of the lead because I didn't use delta, so it's around 49, but okay, maybe it's 47, maybe 51. What are the standard values of capacitance? So it's one of those values. Okay, so these are the components that we have, and here we have also at the terminal we have a resistor which has a very high resistance. I measured it, it's approximately 500 mega ohm. In a separate video I will show you how to measure very large resistances using your multimeter, but this is around 500 mega ohm. Now I will show you the schematic of this circuit. Now I'll show you the schematic. So basically this is the primary side, so here is the feedback winding, this is the main primary winding. The wire of this primary winding is thicker than the feedback winding, as I mentioned also in the previous video. So then there is this feedback which comes to the gate of this transistor, and this is the capacitor which damps the spike of the voltage. And then this is the structure, basically how the connections are made. So we have two blue capacitors, 100 picofarad. We have three diodes. These diodes are probably 10 kilovolts. The blue capacitors are also 10 kilovolts, I guess. This is 500 mega ohm. And there are three red capacitors which are connected in series, and this is basically directly at the terminal, at the output terminal. Now the value of these capacitances is something in between this range, maybe 7.5 or maybe 8.2, maybe 6.8 nanofarad. Now based on these values that we have here, if we have 7.5 for example, so three 7.5 in series will give us 7.5 divided by 3, which is 2.5 nanofarad. So if we calculate this RC time constant, so we have 2.5 nanofarad multiply 500 mega ohm, this gives us approximately 1.25 seconds. So a time constant for this circuit is 1.25 seconds. Usually we wait 5 times time constant, and in that case the voltage would decay, 99% of the voltage would decay. So actually if you charge this generator and then you wait for 5 more multiply 1.25, which gives you approximately 6.25 seconds. So if you charge the generator and wait for 6.25 seconds, then the voltage of the terminal would sufficiently decay that you will not get a shock. I'm going to prove this by doing this test. Here is what I said. So basically time constant R multiply C, 1.25 seconds. 5 tau is 6.25 seconds. The voltage, the output voltage at T is equal to 5 tau is less than 1% of the output voltage at the beginning. Okay, so I increased the distance of this generator. This is a good generator, and I'm going to charge it, applying power to the primary side, and then within 6 seconds I will touch the terminal, and hopefully if my calculation is correct, then I should not get a shock. Okay, let's charge it. 1, 2, 3, 4, 5, 6. So you see that I did not get a shock. But if you do it within 1 second or maybe 2 seconds, you will get a shock, which is not pleasant. Another time. 1, 2, 3, 4, 5, 6. Wow! This was not sufficient. I think I counted it very fast. Another time. I need to check it. Wow. This was really bad. Another time. Let's see. My calculation must be correct. Let's see. Another time. 1, 2, 3, 4, 5, 6. Okay, it was very mild this time. So maybe we need 7 seconds, or okay, one time more, 7 seconds. 1, 2, 3, 4, 5, 6, 7. Okay, so it does not shock me. So after around 7 seconds, 6 to 7 seconds, the charges would reduce sufficiently that it would not give you heavy shock. One thing that's worth mentioning is that the packaging of these generators is really tightly made. It's nicely done. Basically here we have the transformer packed and then these output capacitors. So actually they use these large capacitors at the terminals because they want to have a sufficiently large amount of spark. So these capacitors, they are very small, 100 picofarad, but these in total they create approximately 2.5 nanofarad, which is sufficiently large to create a good discharge. So one point to consider is that these three capacitors, they are connected at the terminal, and at the terminal we can have a voltage of order of 20 kilovolts maybe if you increase the distance between the output terminal. And in that case these three capacitors will be severely stressed. I don't know the rating of these, I could not read anything on them. The skin of them was softened by acetone and I could not separate it from the epoxy. But typically these capacitors, they are few kilovolts, maybe 2 kilovolts or max 3 kilovolts. So I don't know how these three basically can handle 20 kilovolts. Maybe that's why if you run this generator for a long time, it actually burns at the end. And then one failure mode is that it doesn't completely burn. It basically weakens the output spark, and in that case maybe these capacitors become lossy, and basically you will not be able to build high voltage at the output. Another thing to pay attention is that in the arc generator we see that the transistor has a heat sink, as you can see here, but in this case the transistor, the item that is there, it does not have a heat sink, and also the transistor doesn't have a name on it, so I don't know what exactly that transistor is. Maybe it's a MOSFET or whatever that is, but this one does not have a heat sink. So if you pass a large amount of current for a long time, this will overheat and eventually will burn that transistor. So that will be probably another mode of failure. So we have this one may fail. These capacitors are very likely to fail because I am very doubtful that they can handle the actual output voltage of maybe 20 kilovolts. So if you increase the distance at the terminals, you're likely to burn the device. And another thing is that these ceramic capacitors, these 10 kilovolts capacitor, they are not designed to handle high frequency signals. So of course normally if you have a DC in the multiplier, these will not get a very large amount of ripple, but in case you have many of these discharges at the output, these capacitors will also suffer a very high amount of ripple on them, and that can also cause breakdown of these capacitors. I will show you these things that I say on the simulation so you can clearly understand what happens when you have many discharges at the output. Then these capacitors will suffer a high stress, high frequency, higher stress, which can break them. I don't think if the diodes or this resistor or transformers, these are solid stuff, they will not get damaged most likely. Okay, so before I show you the simulation, once more we look at this circuit. So now if this schematic that I draw is correct, which 95% is correct, then if we measure the capacitance from this terminal, we should be able to see the equivalent of these three capacitors, and also partially these two capacitors will also impact at the total capacitance that we see from here. But these three are much larger than them, so we will see basically the equivalent of these three capacitors, almost. And these two will also contribute because these diodes are not completely open in half cycles when we measure the capacitance. Okay, so I first measured this one. This is a module very similar to what I opened. So let's see what is the terminal capacitance. So this gives me approximately 2.45 nanofarad. So if I consider that 2.4 is from these capacitor and 0.5 from these capacitor, let's say. So 2.4, if I multiply by 3, then gives me 7.2 approximately. So each of them is maybe 7.2 or probably 7.5 or so, in that range. So the numbers that I wrote here, they are more or less correct. Okay, so now the other one, I bought it recently. So if I measure this one, okay, so you notice that this one is 2.27, 28 almost, 2.27. So if I multiply this 2.27 by 3 to get the capacitance of one of them, because that 2.27 is the equivalent of all of these. So if you multiply by 3, it gives us nearly 6.8. So I assume that in this newer version, the capacitance that we have, these red capacitors, they are 6.8 nanofarad, 3 of them. Okay, so I decided to test whether the generator works or not in this situation. As I explained before, in the actual generator we have these 3 film capacitors which are connected at the output across this high ohmic resistance. But in this case, these film capacitors are already damaged during the dismantling the module. So I will replace those film capacitor with another 20 kilovolt ceramic capacitor. So now if I apply voltage to the primary, actually surprisingly this module works. So okay, so now it doesn't work. Why? Because the input is shorted. Sorry. So now if I increase the voltage at already 2.5 volt, it starts to spark. And if I go high, at 4 volts, 5 volts. So basically, the generator works in this condition. Now, one thing that I also noticed is that the arc generator transformer is bigger than that transformer. So this transformer most likely cannot produce the same voltage as this one, even though size is not related to the voltage, but I assume that the turn ratio of this transformer is smaller. So if this one can produce 6 to 8 kilovolts, this one probably can produce 5 kilovolts, 6 kilovolts. So then we have a tripler, then we get maximum at the output 18 kilovolts, but of course there is some reduction in efficiency. We will not get 100% efficient system, so we will have maybe 15 kilovolts at the output. So then these film capacitors should handle 5 kilovolt each, which is still I'm very doubtful. Maybe they can handle 3 kilovolts, but 5 kilovolts I'm not sure. Alright, so this is the demonstration that this one works actually. So this is the original module, and this is the internal construction together with this. Okay, so now to see the input waveform, I connected the oscilloscope to the input of the transformer to the primary side, and here is power supply that is connected there. So I apply the voltage. So we can see that this is basically the primary waveform. Now the frequency of this is nearly 44 kilohertz. Unlike the arc generator, which the frequency was 20 kilohertz, so the oscillation here happens at higher frequency. And if I change the magnitude, so if we go up, so at 1.1 volt it draws 110 milliamps. If we go up, close to my hand, at approximately 1.7 volts, the primary side has a voltage of 10 volts. This factor is 1. The probe has, let me go down, this one is creating noise. So this one is set at 1x, so the primary voltage gets a value of around 5 volts at 1 volt, and around 10 volts at 1.6 volts, and around 15 volts at 2.2 volts. Okay, so this is basically the waveform that we have. Maybe I can even measure the voltage right now at the output. To measure the output voltage I need a voltage divider with extremely high input impedance. And if I want to just assemble a few resistors together to make a voltage divider, that would not create the high resistance I want. I need to assemble many 10 mega ohm resistors in series to at least be higher than that resistor that is connected directly at the output. And I do not have a proper probe, a high voltage probe right now. So I cannot measure the output at this moment. I'll postpone it for other videos. One thing to notice is that when the voltage is lower, the frequency is higher. Right now, for example, it's 60 kilohertz. And if I increase the voltage, the frequency gradually decreases. Right now it's 44 kilohertz, and if I go higher it's 35 kilohertz. Okay, so I made a model according to the schematic that I showed you here in Matlab Simulink. These components are all ideal components. We have 3 diodes, 2 capacitors. These are the blue capacitors, 100 picofarad each. Here we have 3 capacitors, the film capacitor. I put the value 7.5 nanofarad. So they are in series. Totally we have 2.5 nanofarad here. And this is the output resistance, which is 500 mega ohm. And this circuit can simulate the discharge. This is not a real simulation of discharge, but basically I trigger it at certain time to create a short circuit across the terminal, and then I open this switch again so the voltage can build up. This is a representation of the secondary of the transformer. So I put a voltage source, put the frequency 35 kilohertz. Now the magnitude I put it 1000 volts, but this is a reference value, so we can change it later. For example, in reality, maybe transformer produces 8 kilovolts. Whatever value that we get, we should multiply it by 8. And the transformer has some resistance. I put it 600 ohms. Now in this case, the source voltage is a sine wave. So basically we have a sine wave on the secondary, and then it feeds to this voltage tripler. Now based on our knowledge, this circuit should produce an output voltage of approximately 3 times than the input. Alright, so let us run the model. Basically the blue one is the input voltage that we have here at the output of the transformer, secondary side of the transformer. The green one is voltage across the first capacitor, the orange one voltage across the second one, and that yellow one is the output voltage. So we see that the output voltage goes 3 times than the input voltage, and this is how the voltage would evolve across this voltage tripler. Now I stop the simulation. I can zoom in. Now we see that, for example, here we have the sine wave, sine input, first capacitor, second and third capacitor. The output of the transformer is probably not the sine wave. As we saw on the oscilloscope, the input signal is completely different. So the output will not be a nice sine wave. Now this is the waveform that we got from the oscilloscope. So I imported in Matlab. And this is basically the waveform. Now this is on the primary side of the transformer. When it feeds to the transformer, on the secondary, if we assume transformer is ideal, then we should have the same waveform on the secondary. But obviously these transformers are not ideal. It has a lot of capacitances on the secondary side, and also we have large inductance there. So basically large leakage inductance, it will filter the signal. So on the secondary side we will not get this signal. But assuming that we have this signal on the secondary side, then we see what happens. Here in the original case, when I simulated it with the sine wave, we see that voltage goes up to almost 3 times than the input. Of course, these components are all ideal. If the components are real, then this value will not be the case. It will not go to 3 times. It will go maybe to 2.6, 2.7 times, depending on the components. Alright, so now what I do is that I'm going to apply that waveform into the voltage tripler, and we see what happens to the output. Same magnitude. I will disable this. Comment out. So if I run this simulation right now, this one is actually the peak value of the signal is now 1000 volts as before. But what we can observe is that the output voltage will not go to 3000 volts. Actually, the output voltage will only reach to 1500 volts. I did the simulation before. And because obviously the waveform that we have, it is not a full sine wave. It's just for a very brief moment of time it peaks, and then the rest of it is actually very small values, as we saw in this waveform. So basically in this case, this voltage tripler will not produce exactly 3 times as the peak value of the input. Will only produce almost 1.5 times than the peak of the input. Okay, so I stop this simulation, zoom in, zoom in. So this is basically the input signal. This is the voltage of the first capacitor. It's not heavily stressed. The second capacitor is 1.2 times than the peak value, and the output is 1.4, 1.5 times. So this suggests that even if the output of the transformer is 8 kilovolts or maybe 10 kilovolts, the output of the generator will be 12 or maybe 15 kilovolts. That is probably the range of the voltage that generator produces. Even at 15 kilovolts, I think these 3 FEM capacitors cannot handle it. So in case you increase the distance between the output terminals and you apply 4 volts, 5 volts to the primary of this generator, with sufficient amount of current, you are going to break this generator maybe after 2-3 times of use. In fact, after I done the shock test, I observed that after few times of use, that generator was already broken. So I repeated the shock test with another good generator, and that 6-7 seconds is okay. It works. But of course, in this time, I did not increase the voltage of the primary too much, and the distance between the terminals, I kept it at 1 centimeter. All right. So now let us continue our simulation. So we have done it for the case where we use this input pulse, and we observe that that is how the voltage increases. Now if I apply breakdown, let's say after 4 milliseconds, so the voltage would rise, and then after 4 milliseconds there would be discharge, and then again the voltage would build up. So here I am going to create, or maybe 3 milliseconds. Normally the time between the discharges are maybe several milliseconds, maybe 5 to 10 milliseconds, even more, 20 milliseconds, depending on the gap distance. But in this case, we see that the voltage build up is rather quick. Within 8 milliseconds, it already builds up to the full value. So if the gap distance is smaller, it breaks down actually when the voltage is not at the full output value. Okay, so now I run this simulation. We see that voltage goes up, and at 3 milliseconds the voltage drops, and again it goes up. So this is basically what happens to the voltage of the other capacitors and the output voltage when we have discharges. Of course, this is not a good model for discharge, but just to demonstrate the voltage variation on the other capacitors. Now these ceramic capacitors, the blue one, these are DC capacitors, so they do not like high voltage, high frequency stress. If you apply high voltage, high frequency stress on them, the capacitance value will quickly decrease because they overheat, the capacitance decreases. And if you keep doing this, the lifetime will reduce and eventually they burn. Now you see that when we have multiple discharges, these capacitors, they suffer, I turn off the input. So they suffer a lot of high frequency stress, which are not designed for. So I assume that if you use this generator for a very long time, they are also going to degrade and eventually maybe they fail. Now, a normal operation, of course, the voltage of these capacitors will go and reach to a DC value. So the stress over them will be DC. But if they have repeated discharges at the output, then this will be the stress which these capacitors are not designed to handle. Now, another thing to notice is that these capacitors, all of them, even if they fail, still they show a value of capacitance, maybe even 60-70% of the original value, or sometimes even the same value as the original value. But actually what happens is that the leakage resistance of these capacitors will be decreased. Now, when you measure the leakage resistance with low voltage, you do not notice it. You maybe notice that from several gigaohm, it reduces to maybe 1 gigaohm, 2 gigaohm, but you do not notice clearly. But when the high voltage stress is applied over them, because this conductive pad that is formed within the capacitors, they are field dependent. So when the electric field is high, then more current can pass through them. It's not linear, let's say. And therefore, only when you put them inside a high voltage circuit, they do not perform properly. But when you measure them with a multimeter, then you see that they more or less behave as a capacitor. All right, another thing that I want to mention, I disable this discharge. So when we run this one, we see that, of course, the voltage builds up and reaches to its final value. Now, if you want to measure I stop these. If you want to measure the output of this generator, because here we have a 500 mega ohm resistor, you must use a probe that has much higher value than this, at least a high voltage probe with 1 giga ohm. Because if the probe that you use here it has a small value, for example, in this case, we notice that the voltage goes to near 1450 volts. But let's say if you use a probe which has 10 mega ohm. So what happens is that the probe itself will add a load to this. Let me add this extra resistor here, and now this extra resistor is 10 mega ohm. What will happen is that the voltage will not reach to what it could reach without the probe, so it has decayed a bit. If you want to really know the output voltage, you have to use a probe that has rather high input impedance. But actually in this simulation it shows that the voltage drop is not significant. So even a 10 mega ohm probe will show more or less the final value. So if your probe has maybe 1 giga ohm input impedance, a high voltage probe, usually they have 1 giga ohm, then you can measure this very accurately. Alright, I think this is enough for this video. I hope that this information is useful for some people on this planet. Bye!